Thanks to the organizers, Purushottam, Shauli, and Thanga. Okay, all right, very good. I'm very happy, glad. And once again, happy birthday, Ram. Live long, with the tribe of mathematics and your all the help that you give to Indian mathematics and Indian mathematicians. I hope it continues, and we're all very grateful. I personally am very, very grateful for your mentoring over the years. So I want to talk about special values of L functions and congruences. So let me just make some motivational comments, especially since there are many students, and by the way, I'm very happy to say that there are lots of ICER students here. For those of you who aren't familiar with ICER, those of you who come from abroad, ICER is one of these new brand of institutes in India. It's called Indian Institute of Science Education and Research. There are 5 of them. I am heading the mathematics program in ICER Pune, and from ICER Pune we have a huge presence here. There are 4 faculty members, I think 3 undergraduates and 2 former undergraduate students who are now doing their PhDs abroad. So since there are several students and from an ICER particular, so I want to make some general comments. Now take any L function that you like. In fact, take an element in the Selberg class. Take any L function, Riemann zeta function, Dirichlet L function, Hecke L function, modulo forms, L function of those, Langland-Shahidi, whatever. Take a favorite L function. To begin the story, you need to have some basic analytic theory in place. So typically these are defined in some half plane, like a Dirichlet series, or maybe as an Euler product. That might be the definition. Then you got to continue it, maybe prove Euler product exists, and then prove a functional equation, maybe bounded in vertical strips, and so on. So this is the basic analytic theory. Once this is in place, you can go in 2 different directions. You could study advanced analytic properties. So we saw in Jeff Hofstein's talk, you can study subconvexity, or for example, I think Rita Munshi also talked about subconvexity, or non-vanishing of L functions, non-vanishing of twists, and so on, so on. The other direction is you can talk about arithmetic theory, in the sense that you can look at the Riemann zeta function and you can look at zeta 2. Zeta 2 is pi squared times a rational, zeta 2m is pi to the 2m times a rational. This I would like to call as arithmetic theory. If you have proved that for your favorite L function, then you can go on to what one might call advanced arithmetic theory. You can ask zeta 2 by pi squared is a rational, what sort of primes divide that? And what finer arithmetic information is contained in those kind of L values. So my talk is roughly in that direction. There will be some L function, and I'll be looking at certain special values. One will identify the analog of pi squared, so that one has an L value by this kind of analog of pi squared is rational, and try to understand what sort of arithmetic information is contained in the set of primes which divide that algebraic quantity. So a theorem, to get started, suppose I take a f which is a weight k cusp form of some level and some Nebelian triples, doesn't matter, and I say it's primitive. So what's going on? There is this theorem originally due to Hida. One might say this was Hida's first claim to fame, which goes roughly like, if a prime p divides some suitable L value attached to f, then this prime is in fact is a congruence prime. Of course, this is a somewhat vague statement, so I got to make things precise. Which L function am I looking at, which L value, and so on. So here one looks at the value at 1 of the adjoint L function. This is a degree 3 L function that you attach to f. This itself is maybe transcendental, and then you have to divide by some periods. This then is an algebraic quantity. One might call this as the algebraic part of this adjoint L value at 1, and if p divides such a thing, then one would say p is a congruence prime for f, by which one means that there exists a g, another weight k level and form, so that and one can even say that g is not f or any conjugate of f, so that the congruence condition is that the coefficients are congruent, an of f is congruent to an of g mod p. So such a theorem, this is a famous paper of Hida in Invenciones in the early 80s. He proved this theorem for elliptic modulo forms. And then later, here's a bit of history about this theorems of this type. His student Eknath Ghate proved an analogous theorem for Hilbert modulo forms for parallel weight. This is a paper in Compositio, I don't know, 2000 or somewhere thereabouts. Later, this was further generalized by Mladen Dimitrov in his thesis that he wrote with Tillerson. This is a paper in ENS sometime, I don't know, 2005 comes to my head. And then Eric Urban, actually before these two, did this for GL2 over an imaginary quadratic field. There's a theorem along these lines. And recently, what is the name? Namikawa. Recently, we got to know that a certain Japanese mathematician, Namikawa, has done this for GL2 over any number field. So this entire history is all about GL2 over various special fields and then finally for any number field. So my take-home message in this talk for you is now in collaboration with my smart young colleague Baskar Balasubramanyam is sitting there. Baskar Balasubramanyam. We can do this, prove an analogous theorem for GLN or any number field. So this is a preliminary report. This is just fresh, hot from the oven or something. This is the first time I'm giving a talk on this project. So this talk is really a preliminary report on this. Not all details have been ironed out, but we certainly have, I think, almost most of the details to feel confident enough to give a talk on this work. Okay, so this is the history and where I'm what I'm going to talk about. So, like I said, to get started with any such what might come under advanced arithmetic theory, I need to have the basic analytic theory of the relevant L functions in place. So let me just touch upon the relevant analytic theory. Analytic theory of, this is really Rankin-Selberg, and from that one juices out adjoint L functions, Rankin-Selberg L functions for GLN cross GLN. So this object is now replaced by, I start with a pi and a representation space V pi. This is a cuspidal automorphic representation of GLN of AF. And pi tilde, to begin with, pi tilde, V tilde is another representation of the same kind, but later I will specialize to the case when this is the contragradient of pi, the dual representation. And one could consider, so I take a cusp form, for pi, I take a cusp form for pi tilde, and one considers an integral, I'm going to denote it by d s phi tilde, and there's another auxiliary data, capital phi, which is an integral over GLN A AF mod GLN F mod the center center AF of, I integrate these cusp forms against each other. If I just did this much, then this might degenerate to 0. So you know in the Rankin-Selberg, the genius of both Rankin and Selberg independently was to throw in a certain suitable Eisenstein series, which depends on this data, and then there is some central character. It doesn't matter for this top level discussion. So you consider an integral like this. And then from the wisdom that we now have from Jackie Langland's, such an integral, these are cusp forms, they rapidly decay. This integral makes sense, it's very good to analyze functions as a function of S. However, this is not Eulerian. It doesn't, you can't see how it factorizes over all the places of the number field. So you jump across to the Whittaker models at some other function space, which is kind of, you replace V pi by that, and there's a standard set of steps that you go through, and this is typically called unfolding. And you write this as a certain product over all places V of a certain local integral, I'll just call it psi V, of the Whittaker vector attached to phi at V, and likewise phi tilde at V, and something else, and this data. And if I've taken my cusp forms to be nice, so what I mean by that for the experts is in the Whittaker model, the local vectors are new vectors. And this is basically the L function of pi cross pi tilde. That's what you'll see, basically, okay. Now I'm going to assume that pi tilde is in fact the dual of pi. And this L function, this Rankin-Selberg L function factorizes as the Dedekind zeta function of f times whatever comes, I'm going to call this, or maybe to make my notation compatible with the notation I think in Ravi's talk, which is really Langlands' notation, the R, he had a representation pi and a representation R of the dual group. That representation is add circle, which is the representation of the group GLNC on the Lie algebra SLNC. So I think he put the R at the anyway, never mind. So I look at this adjoint L function. All right, now I'm in the situation where this pi tilde is in fact the dual of pi. The technically correct word would be contragradient of pi. And you realize that the Dedekind zeta function has a pole at s equals 1. So you compute the residue at s equals 1 of this quantity. And you do this in two different ways. On the one hand, if you compute residue at s equals 1, it's the residue of this guy at s equals 1, it's some number, whatever it is. So what you see is essentially the Peterson norm, the Peterson inner product of phi with phi tilde. So on the one hand, this is essentially phi tilde. On the other hand, you go through all this, and I compute the residue at s equals 1. This is, that pole comes from here. This you know what it is, class number, regulator, blah, blah, blah. And then the value at 1 of this add circle. I'll simply call this the adjoint L function. Bear in mind that it is really this add circle in the sense that here this is a degree 3 L function, not the degree 4 L function. And so on the other hand, this is essentially L1. And if you put these together and you are careful about what this essentially means, then you get a statement like this, that phi, the Peterson norm, Peterson inner product of phi with phi tilde is the product over Archimedean places of some quantity which is usually hard to compute, divided by a quantity which depends only on f, which is coming from the residue at s equals 1 of the Dedekind zeta function, times a number which depends only on the ramified places. So this is the essentially part, times L1. So this is a certain analytic statement about this special value. And the game that one needs to play to prove a theorem like this, well, in fact, before you can prove a theorem like this, I need a theorem that this L value by some suitable canonical periods is in fact algebraic. So first one's got to prove an algebraicity statement for this L value. Once that is in place, one can hope to ask, can I prove a theorem like this? So the game to prove an algebraicity statement for this particular L value is to take this formula and you stare at it and you throw, put a sort of geometric spin on this analytic statement. So you want to interpret this in cohomology. And that takes some work. So I want to now introduce the relevant ingredients to see this somehow captured in terms of certain maps in some cohomology groups. So maybe the next 10 or 15 minutes I'll be talking about how one can interpret this in cohomology. So I got to introduce some basic ingredients which usually go by this title, Cohomology of Arithmetic Groups. So I'm going to let G, well, G is, okay, I said GLN. So G is going to be restriction of scalars of GLN. It's somehow easy, for some technical reason I'd like to work with a Q group, that's all. So G is GLNF. Inside this, I can take the restriction of scalars or the standard upper triangular, that Borel subgroup, I call that B. Inside that is the restriction of scalars or diagonals, called that T. Inside that is the center of G. And inside that is the center of the center, in the sense that if I take the restriction of scalars from F to Q of GM, inside that is a copy of GM over Q. And let me call that S. So this S is isomorphic to GM over Q. All right. I take a level structure. KF is, this is just an open compact subgroup. This is like your gamma naught n. I consider the space, hang on. I take K infinity to be the maximal compact at infinity, but slightly thickened. So this is the R points of S. So this is a product, it's like the diagonal R cross sitting inside the R points of the center, times the product over maybe real places I throw in ON, that's the maximal compact of GLN, and at the complex places I take UN. And you should keep a certain small but very important technical point in mind, that I'm going to look at the group of connected components of K infinity. So this is just K infinity mod K infinity circle. And if you work this out, this is simply UN is connected, by the way. So this is the product over real places of ON mod SON, and which is just Z mod 2. So the product of Z mod 2s, as many as the number of real places. And this is going to act on many things to come. We just bear that in mind. Okay, I define the space SGKF. This is GA mod GQ mod K infinity circle KF. This is just a jazzed up version of your modular curve, upper half plane mod a discrete subgroup in the context of GLN. All right. It's if this KF, if there is no pinching, no elements of finite order or something, this is a locally symmetric space. Otherwise, it's almost a locally symmetric space. I take a, what else do I need? I take a weight, let me call this mu. I take a weight, and let's say I take a dominant integral weight, call it mu, and I take the corresponding representation m mu. This is the algebraic, I suppose I should say absolutely irreducible representation of the algebraic G, group G over Q. And this m mu gives me a sheaf. I'm going to denote that m mu tilde. This is a sheaf on SGKF. This is an algebraic representation of the algebraic group G. It sort of works rationally. There is a small, you may not be able to see this representation over Q itself, but you got to go up a little. A field somehow, I'll just call this Q mu. If those of you who are familiar with Hilbert modular forms, you might have a bunch of weights K1, K2 through Kd. If D is the degree of the extension, then you look at how Galois Q bar over Q acts on this, and you take the fixed points. You got to go up a little. In any case, I'm going to ultimately consider some number field E, which will contain these sort of fields floating around, and I'll take this to be Galois. So this representation will be defined over E, and this would be a sheaf of E vector spaces on this locally symmetric space. And people who study cohomology of arithmetic groups, the basic object of interest, is the cohomology of such a locally symmetric space with coefficients in a sheaf which comes out of a algebraic irreducible representation. This has a tremendous amount of geometry, but number theory and L values and all this. So the game is to somehow juice out information, number theoretic information from these cohomology groups. It's defined over E at the moment. A related cohomology group which plays an important role is, well, I got some sheaf. I can look at global sections with compact support and take the corresponding cohomology group. So that's and the image of cohomology with compact support inside full cohomology, that's usually called inner cohomology, and one denotes it by putting a shriek. Some people call it interior cohomology. And those of you familiar with Eichler-Shimura, this is the same as parabolic cohomology, which in Shimura's terminology. Yeah, you got that. So this is inner. This E is some floating field. Now suppose I just went all the way up to, yeah, maybe I should do this on another board. I need some more space. Now let me just go all the way up to complex numbers. And inside this is inner, and inside that sits what's called cuspidal cohomology. If you think of this, here's a space, here's a sheaf. If you want to compute sheaf cohomology, you take some resolution. You might work with a Dirac resolution and think in terms of differential forms. These are those cohomology classes which are captured by cusp forms. Yeah? And so here's where enters the number theoretic information. And this guy breaks up as a direct sum in terms of contributions coming from cuspidal automorphic representations. So any representation pi which contributes to this, okay, so where is the representation? What's the action? I should have said this right here. On this space is an action of the Hecke algebra of G relative to Kf, as well as the group of connected components. And you think in terms of, you forget the level structure, it's as if like GAF is acting on this group, this cohomology group times this group of connected components. So there's a bunch of representations which show up, the finite part, and they might show up with some character associated to this, the K infinity. And any pi which contributes to this, there's a notation, it's a cohomological representation of the group G with coefficients in mu. If you play this with GL2 over Q, and I take my weight, I fix an integer K, and I take my weight mu to be K minus 2 times half the sum of positive roots, then what shows up here are exactly the representations attached to holomorphic cusp forms. Mass forms don't show up in this game, so they are not arithmetically interesting in the sense that they are not of motivic type. That's the way one would say this. I didn't specify what degree I'm looking at. That one has to worry about what degree. And this appearance of this Hecke modules, I'll just denote this by h dot pi f cross epsilon. Just an ad hoc notation here. On the other hand, I already mentioned that one can talk in terms of the Whittaker model. I can look at the Whittaker model of pi f, and this is a kind of souped up version of the Eichler-Shimura isomorphism. This is isomorphic to one of these simply as a GAF module. There's a choice of epsilon. This epsilon, again, if it work in terms of GL2 over Q, epsilon is just O2 mod SO2. So that's just Z mod 2. And if you look at Eichler-Shimura from the space of holomorphic cusp forms, there are two maps. They would usually denote theta plus and theta minus or something. So that's this epsilon. For every epsilon, there is an isomorphism of this kind. And one can look at this situation. And here is some bare bones linear algebra, which is going to be invoked in a second. It looks like, suppose I got a vector space V, say, over complex numbers, and which is isomorphic to the vector space W over complex numbers. And let's say these guys had some rational structures. So let's say this, there's a V0, over E, a rational structure here, and likewise W0. And let me call this isomorphism F. This F, you can ask, how does it behave relative to these rational structures? If I take this F applied to V0, I get another E structure on the other side, and I can ask myself, well, is this equal to the E structure there? And this is not just vector spaces and rational structures, but there is an action of some group, irreducible action of the group GAF. And because of the irreducibility of this action, there is some uniqueness principle which one can prove, and one sees that rational structures, if they exist, are unique up to homotheties, and that defines a period. Maybe, yeah, that defines a period. So I should say there exists a PF, a non-zero complex number for which this happens. So if I worry about which cohomology degree, if I take this to be the lowest possible degree, then the corresponding number which comes out, I would denote this P epsilon pi f. This is a certain non-zero complex number which is capturing, capturing rational structures, whether it translates one to the other or not, and in the highest degree, I'll just call it Q epsilon. And these are what I have previously called in some of my papers Betti-Whittaker periods. This is the Whittaker part, this is Betti cohomology. So these are the periods which are going to show up in this L value divided by periods is algebraic. These are some numbers which are going to show up. So now, how would I interpret that analytic statement? You remember that analytic statement that the Peterson inner product between two cusp forms is basically the L value at hand. The interpretation of that in cohomology comes, when it comes to this, I like to sort of think about this in terms of one diagram. So in most of these cohomological proofs of special values of L functions, typically there is one diagram which sort of captures the essence of what's going on, and that diagram looks like this for the situation. So remember, I got myself a cuspidal automorphic representation, but then to play this cohomological game, I got to assume it's of cohomological type, and there's some weight mu, and I got its contragradient, which is also turns out to be of cohomological type relative to the dual weight. I consider the Whittaker models of pi f and pi tilde f, and I can map into cohomology, and this lowest possible degree in which I see cuspidal cohomology, let me just call that B, and the highest, the top degree, I call it T. If you work with GL2 over Q, both these degrees are 1. If you work with GL3, I don't know how to do this calculation, I think they're 2 and 3. GL for a Hilbert modular form or a degree D, totally real field, both of them are D. But for GLN or a number field, you can write them down. There are some 2 numbers. So on the one hand, I look at cohomology in the lowest degree, cuspidal, which sits inside inner of this locally symmetric space with coefficients there. Across here, I go to top degree. I go there. On the other hand, I can take a Whittaker vector, a special nice vector, there's new vectors everywhere, and I go patch on something at infinity. What I patch on at infinity comes from some cohomological reason we need not get into. I can go into the space of cusp forms for pi, and likewise I can go into the space of cusp forms for pi tilde. And here I have the Peterson pairing. So this is my phi tilde business. And here what happens is this bottom, the lowest degree in which I see cuspidal cohomology and the highest degree in which I see cuspidal cohomology, lo and behold, B plus T turns out to be the dimension of this locally symmetric space. And these are represented by compactly supported forms. So if I cup them up or wedge them up, however you want to think, I get a cohomology class in top degree on an orientable manifold. These manifolds are nice, and the local systems of one is the dual of the other. There is a certain Poincare duality at play, and Poincare would give me that I can go to C. And, well, everything matches up. And the point of doing this, so this is the cohomological interpretation, and the point of doing this is Poincare duality. This bottom arrow, all of this works rationally. You put all these thoughts into place and then you clean it up, and then you get the following theorem. So this is the first main theorem. So theorem is, so let pi be a cohomological representation of G. Remember, G is GLN over F, or really restriction of scalars, etc. I got a highest weight mu. Then for every Galois automorphism, I can take all automorphisms of C as a field. If I look at the quantity L1 of the adjoint L function and I divide by a bunch of things, I divide by that omega f, which is really coming from the residue at 1 of the Dedekind zeta function, a bunch of quantities from ramified representations, from the ramified places, the ramified finite places, these periods p epsilon pi. In Poincare duality, how does this work? If I have taken orientable manifold and I look at a cohomology class in top degree with compact supports, and I just map it into C, how do you map? You fix an orientation on the manifold and you just integrate it. So I fix an orientation on this manifold. And then I got to worry about how the group of connected components acts on this orientation. And so there are these epsilons, this painful epsilons floating around. I got to take, if I take the period in lowest degree for a certain sign epsilon, I got to take the period in highest degree for a certain complementary sign for the dual representation. So epsilon is any sign character there, and epsilon tilde is, one is forced to take it to be this. If not, it just degenerates to the 0 map there. So I do that, and there is some junk which comes from infinity. I'll just call that p infinity pi. In an ideal world where you can compute anything, one expects this to be some power of 2 pi I. The pi in the 2 pi I is different from this pi. This is a representation. 2 pi I, that's 3.14, etc. Yeah. So you look at this L value divided by all these guys, and the statement is this is well behaved under Galois automorphisms. In particular, if I call everything that you see inside, if I simply call this as the algebraic part of the adjoint L value, and I could pick any one of the signs epsilon, then in particular, one is asserting that this is suitably algebraic, and if one is careful, moreover, if I have carefully defined my periods, then this algebraic part lives in a certain field. So I got Q, I went up, my mu gave me a certain number field, Q mu. This Q mu itself sits in a slightly larger field, I'll call that Q pi. This is the analog of, if you take a modular form, which is nice, and I adjoin all the Fourier coefficients, the field you get is a number field. So this is the analog of such a number, the representation theoretic analog of such a number field. And I just take an extension E, which is Galois finite and Galois over Q. And if I'm careful with my definition of periods, this lives, this algebraic part lives not just in E, but I could take the ring of integers O in E. And if I'm careful, and so now it makes sense to talk about primes dividing this. Well, even if it's an E, I can talk about primes dividing, primes of E, prime ideals of E dividing such a quantity. Note. Now, if you study the Riemann zeta function, there are formulas zeta 2, zeta 4, zeta 6. Zeta 2m is pi to the 2m times a rational, but whereas you can't make these kind of statements for odd zeta values. Even positive integers and odd negative integers are what are called critical points. They have got to do with the poles of the corresponding gamma functions on either side of the functional equation, and odd positive integers and even negative integers are non-critical points. This is, you can ask, is this a critical point, in terms of which you can define what is a critical point, and note L1 add circle pi is critical, is a critical value if and only if I'm working with GL2 and f is totally real. In fact, Eric Urban in his paper GL2 or an imaginary quadratic, he makes this observation. He says this happens to be a non-critical value. So this is in the world of Deligne's conjecture about special values of motivic L functions, as long as I'm working with Hilbert modulo forms. And if I'm not in this situation, it's not so much Deligne, but we are somewhere in the world of Beilinsen's conjectures. Yeah. Say this again? Yeah. Yeah. So now I'd like to I don't have enough time to develop the relevant how this gives statements about congruences, but let me at least put down a statement. So this is the first theorem, theorem 2. So again, my data at hand is a representation of cohomological type on GLN, and I take a prime ideal of the ring of integers of O, and well, I got to exclude some finite set of primes. Assume P is not in some finite set of. Then this theorem, the statement about congruence, is what I put down, the analog, the generalization. It's a generalization of Hida's theorem that P divides this algebraic part of this L value. Epsilon is any sign. Implies this prime ideal as a congruence prime. One needs to define what one means by this, but one can do that. And roughly speaking, I'd like to, I have about, I don't know, 3 or 4 minutes. I'd like to give some hint of an idea, what is there here. The bare bones linear algebra again is something like this. This is all standard coming out of Hida's work and maybe other like Maser and Ribet. I got a vector space V, say an E vector space, and inside this is a lattice L, an O lattice. Supposing this E vector space, I had some decomposition as V1 directs on V2. In this situation, one can consider what's called the congruence module for L relative to this decomposition V1 plus V2. This is defined as I take this lattice and I go mod, I intersect this lattice with V1 and I take the sum with the intersection of L with V2. So L intersection V1 direct sum L intersection V2. This is the congruence module. A prime P, if it lies in the support of this is telling you that there is something here. There's something in V1 and something in V2, there's something in L intersection V1 and L intersection V2, which become congruent mod P. They become 0 when they're equal to each other when I go look at O mod P. So this is called the congruence module. And what we would do is for V, one takes the cohomology of this space with coefficients in this E. Well, maybe not the whole thing or some part of this, something like this. V1, one takes, I got this pi, and I take the direct sum over all conjugates of pi. And V2 is a supplement of that or complement of that, whatever you say, just a complement of V1. Everything else, all this is happening inside inner cohomology. And the lattice L is integral cohomology, but then there might be torsion, so one works with the image of integral in rational cohomology. So this is the image, and to say image, I just put in a bar there of and one plays around with this picture. And what one proves is, well, actually it's not just, if you, the diagram which was there, I pair cohomology in bottom degree with cohomology in top degree. So likewise, one has to work with V tilde, which is cohomology in top degree, blah, 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 and all the rest of the corresponding statements. And the statement this about congruences falls out of a statement like a prime, this P divides this algebraic part of this L value if and only if P divides, I got a V tilde and I got a corresponding L intersection V1 tilde, or rather I should say L tilde intersection V1 tilde, it divides the discriminant of the pairing L intersection V1 with L tilde intersection V1, something like this, and then you relate that to this congruence module. And by playing around with this, out pops a theorem like this. I know I've gone a little faster, but roughly this is the idea. This is all essentially standard. Whatever was there, the story which was there for GL2, one has to be just careful, and it's just extra bookkeeping. In some sense, to my mind, this was the realizing, working with bottom degree, top degree, what sort of signs to pick, and putting things together. That's the hard part. So I'm done. Thank you.